So part three, part on the hierarchical distributions or hierarchical Bayesian models. And so far we talked about cases, we were calculating this probability over A given B, and A and B would take some finite number, usually, those binary variables, and we were able just to hand calculate everything. The difference in hierarchical models, we gonna change notation slightly. The equation doesn't change, so I'm gonna write down the notations and we'll talk about this. So we're gonna be talking about probability over some theta given, and we're gonna call it, let's say, data for now. And it's gonna be the likelihood probability over data given the parameters theta times the prior for the parameter theta divided by the total evidence over the data. So let's talk about it. What's the difference between what we've done so far? So first part is this one, probability over data given theta. Now here theta is some parameter of a statistical model. And this statistical model is identified by two parts. So the first part is the likelihood. And the likelihood is the same likelihood as you saw in your introduction statistics course. So likelihood is just you assume some distribution over data. So likelihood basically uses distribution over data. And theta is the parameter of this distribution, okay? And when you calculate the product of the probabilities, then you get the likelihood. So I'll write it down a little bit more details. And then you have your prior distribution. And then, of course, you have the evidence, which is total probability. And so let's do a quick example. Let's say we assume that data is just a sequence of observations, x1 all the way to xn. And let's assume that each observation is IID normal distribution with some parameter mu and variance sigma squared. So in this case, parameter theta is just two parameters. It's a vector with two entries, mu and sigma squared. And the likelihood, of course, we know the likelihood, so probability of observing this data set given the parameter theta is the product of normal density functions, right? So it's a product, and so I'm just gonna call phi of xi mu and sigma squared, where phi is just PDF of normal distribution. And so we have n observations, so we're going to product over all of those. So that's the first part of your model. That's the likelihood part. And now in the Bayesian hierarchical model, you have to provide another part. You have to provide this prior distribution over theta, which means that you have to make a guess about what those parameters theta are going to be. And we'll see a lot of examples about it. So you'll develop intuition and you'll see exactly how it's done. I just want to give you a quick, brief introduction of what is coming. And so you basically, another part you have to specify this prior p of theta, so which is, in this case, over mu and sigma squared. And sometimes you don't have to specify prior over both parameters. For example, you assume, sometimes you can assume that sigma squared is known. And then you just have to specify prior over mu. And, you can make it another normal centered at 0 with some sigma mu squared. So you can have a normal prior on your expected value of your likelihood function. Okay, so that's an example. Again, this is just give you a quick overview. If this seems confusing at this point, it's gonna become more clear, hopefully very clear, by the end of this part 3. And there, of course, there are a lot of applications we're going to see. So we will do this Bayes rule and probabilistic learning. We will see how to use computational techniques like Markov chain Monte Carlo and particle filtering. And if you want to learn a little bit more on the hierarchical Bayes models, linear decision making, this is a very this is more like a pop book popularizing Bayesian modeling rather than very rigorous mathematical explanation of it. But nevertheless, I think it's a very good introduction to the way that Bayesians think. And Bernardo and Smith, Bayesian theory. So this is more structured, rigorous introduction to the topic. Again, we're gonna see hierarchical models and MCMC algorithms. We will see some machine learning examples, dynamic state space models, so we'll model some time series. This is a more recent collection of papers published on this topic. And some popular books that I personally like, Theory That Never Dies, Theory That Would Not Die. The nice thing about this book, he talks about history, he talks about the Thomas Bayes. Thomas Bayes was he lived in England. He was not a mathematician. He was what is called a mature mathematician in those days. And the way he described what we call the Bayes rule now, again, it was not very mathematical. He basically explained it as a game. He would sit on a chair, and there would be a table behind, and his assistant would place a black ball on the table, and Thomas Bayes would throw a white ball. He doesn't know where the white ball is landed, but he assumes white ball can uniformly land anywhere on the table. And then his assistant would tell where this white ball in relevance to the black ball. For example, he would say, white ball is on the bottom left of the black ball. So then Thomas Bayes will throw another ball and he'll say, the white ball is on the bottom left. And so he would keep throwing, and the more pieces of information you get, the more relative locations he would get, the more precise he will be about the location of the ball. So let's just think about this. If you always hear left bottom, then he knows that the right location for the black ball is the top right location on the table. Okay, and then he talks about Pierre Laplace, who was a French mathematician, and he is the person who really put mathematical framework around Bayesian calculations. He actually was applied scientist. He was using the Bayesian calculations to calculate trajectories of planets and solar bodies, some objects from solar system. I think it was planets mostly. And the reason that he used Bayesian way is because the number of observations was very small, but at the same time he had a very strong prior about the motion of those objects, because they were governed by laws of physics that were somewhat known those days. So he would use laws of physics as the prior assumption of where the bodies of a solar system gonna be, and then he used few observations that he could get, and then he would use the Bayesian rule to update values of the parameters of the equations that govern the dynamics of those bodies. And then he talked about code break, and there's this famous movie about Alan Turing that came out, I don't know, maybe 10 years ago now, maybe 8 years ago. So he's talking about Alan Turing and code breaking and Bayes' use there. And Bayesian search, he's talking about this Air France example. And Bayesian search actually was applied quite successfully by one of my colleagues, a person who works here in Northern Virginia at a company called Metron, and his name is Larry Stone. He still works in it, and he actually the person who popularized this approach, and he was very famous for applying it to some of those search problems. Bayesian search is in very roughly, so I just gonna explain you. So you want to search for an airplane or a submarine or something that is missing, and you basically start with a area that you think where the airplane should be searched, and you split it. You cover it with a grid, and you basically collect all the information that you can about possible location of the airplane on this grid, and you assign probabilities, right? So you have probability 1 1, so each cell will have a probability ij assigned to it. So probability ij is the probability that plane is in cell ij. So let's say you have I this direction and j index in this direction. And what happens, so you basically pick ij, you pick the cell with the highest probability and you go and search in this location. So let's say it's this location here, okay? And then uh, you spend some time searching, and then the result of the search is that plane was found, and then you stop and the plane was not found. And then you use this information to update all of the pij. So what you do, you assign probability 0 here. So and then you basically update probability over pij for each ij, given that the plane was not found. Let's say you were searching in some location, 3 4, right? So you were searching in location 3 4, you did not find the plane, and you use this piece of information, and then you basically, so for example, location 3 4 was identified as the most likely because of the currents, and then you say, okay, 3 4 was not the location of the plane. Maybe the current did not play a role, maybe some other force played a role that can move the airplane. So you start rethinking how you should update your price in the presence of this new piece of information. So you update your price, and again you solve the same problem. You pick the cell with the highest probability of the airplane being there, and you go search there. So it's all about carefully collecting evidence that you have from experts, from people who know something about where the airplane could be, and then updating those probabilities using this piece of evidence and using the results of the search operation. Nate Silver, who is the editor at 538 now, and he was the columnist at New York Times. He became famous for correctly predicting both of the Obama elections. So he wrote a book on which is called The Signal and the Noise. He talks about using Bayes' rule for his forecasting. The Obama elections was predicted using Bayesian forecasting. So he talks, of course, about elections, things he became famous for, and he also talks about sports, things he's really passionate about. And if you go to this 538 website, those are the main topics that they talk about: sports and the elections. And one of the reasons I like 538 is that they give very good popular explanation of their modeling techniques. So if you want to learn to communicate results of your modeling, of your predictive model, then 538 is, I think, is a good example of how those results can be communicated to the people that are not modelers and don't understand the language of statistical modeling. All right, so Bayesian, so we know that Bayes did it many years ago, and Laplace, but the true explosion of the Bayesian learning started really in 50s when we started having computers that allows us to do Monte Carlo simulations, so we can generate random samples from distributions. And first people to do this was von Neumann and Ulam. In 40s, Ulam was a Polish mathematician, and von Neumann was a Jewish mathematician from Hungary who immigrated to the United States. I think Ulam also immigrated to the United States. And then later, Metropolis did it in 50s. Metropolis was a physicist, and von Neumann was a mathematician, but heavily involved in physics. So the first applications of Monte Carlo simulations actually were in physics when they were trying to calculate integrals that were not able to calculate otherwise high dimensional integrals. And then later on we have Gibbs sampling, Giemann and Gelfand and Smith. So this is 1980s, and I think Gelfand and Smith 1990 or 1991. And then late 90s we have sequential particle filtering. So all of those things, all of the algorithms that involved relatively new by the standards of mathematical theories and mathematical algorithms. All right, and of course, applications are in regularization and sparsity. So a lot of people who work on signal processing use Bayesian learning whenever they want to learn some sparse signals. Hierarchical models that we're going to learn in this class, and shrinkage. Hidden Markov models is quite popular model, and nonlinear, non-Gaussian state space models. So a lot of different applications, a lot of very flexible statistical models can be done using Bayesian approach combined with one of those algorithms. So really, you have to have two things. You have to have the Bayes model, which typically is not that hard. I mean, maybe it's a strong statement, but I mean, modeling is hard thing. But modeling is more of an art. So modeling is first part, and then algorithm is the second part, and you really have to have a model which is computable. And if you ever took optimization course, in optimization is the same problem. You have modeling and you have algorithmic part, and sometimes you can come up with a model that you think is a good description of the subject that you're trying to model, but there is no good algorithms to solve it. So you basically have to go back and find a model that is computable. In Bayesian modeling, you have the same problem. So we will see that high dimensionality can be an issue, and sometimes you have to deal with this, and you have to be practical about the way you formulate your models. All right. And we will talk about probabilistic reasoning. And so one of the differences between Bayesian learning and more traditional frequentist approach is that everything we do is probabilistic, and all the statements we do are probabilistic. And instead of calculating values of the parameters, we're going to calculate probabilities of the parameters. And instead of calculating confidence interval, we're going to calculate credible intervals, meaning the probability that this variable takes 95% probability that this variable, so basically interval in which probability is 95% for this specific variable. And again, we're going to be using Monte Carlo due to von Neumann, Ulam, and Metropolis. We're going to do shrinkage and estimation, and people like Lyndon Smith are really people who started talking about this and pioneered some of the techniques. Smith was the person behind Gibbs sampler, and Efren Morris also wrote about this in about the shrinkage estimation in 70s. All right, so back to the Bayesian inference, the problem of what really Bayesian inference is. So you always start with probability distribution for data given the parameters. So that's your likelihood. So here for data, I just use notation y. So the y stands for the data. So you have some data, you have some observation in hand, and you assume some distribution over this data, and this is some parametric distribution like normal, binomial, Poisson, and you assume some probability distribution for the unknown parameters, probability over this parameters data, we call it prior, and then inference for unknown conditions on observed data. So we want to really find the inverse probability. We want probability over theta given y. So we want to know the posterior distribution, posterior distribution over the parameters of the model given the observed data. And again, as we said previously, that's the difference between the frequentist approach and the Bayesian approach in the Bayes, you end up with the stereo probability P of theta given Y. In the frequentist approach, you end up with point estimate that typically comes from maximum likelihood estimation. All right, so and Bayes theorem really allows us to calculate the posterior. So we just use the Bayes rule. It's a product of the likelihood and the prior distribution divided by the total probability over the data, called evidence. And then this evidence is just so it's the same as probability over data and theta jointly, and you basically have to integrate data. Now, the reason we're going to use the numerical algorithms, MCMC algorithms, is because this one typically is hard to calculate. So typically, it's an integral that cannot be solved analytically. So you cannot use one of your calculus tricks, substitution of the variables, and just analytically calculate the value of this integral. And it's usually, of course, definite integral. So, so you integrate over the domain of your parameter theta. So you cannot typically calculate it analytically. And also when theta is high dimensional, then you cannot really use your numerical integration techniques. So if you ever took a numerical course, or maybe some engineering courses, they teach you a trapezoid rule. This is the simplest way, but there are quite a few ways to numerically calculate values of definite integrals. So those things do not work in high dimensions. So computation, this is a hard problem, and actually MCMC is the way to solve it. So the inference is very different from p-values. We saw the example of hypothesis testing when we talked about the limitless paradox. So basically, the Bayes rule has a lot of implications. The way, for example, you do hypothesis testing is very different compared to the frequentist approach where p-values are used.